Good evening to all. My name is Ganesh Shankar Bhandari, and I am a PhD research scholar in IIT Roorkee, and I am here to take the live sessions for NPTEL course Principles of Extractive Metallurgy, taught by Professor Tarun Kumar Kundu from IIT Kharagpur. Okay, so we will start with the previous week lectures revision. Then, based on the previous week lectures, we will do some MCQ based problems. Uh, and if you have any doubt regarding the previous week lectures, then you can ask those doubts also. Okay, so in the previous week lectures, we have learned about some mass and heat balances for combustion heat utilization in furnace. Before these lectures, we have learned about different types of fuel used in the in the metallurgical operations like coking coal, petroleum, and how to characterize them with the help of proximate analysis or ultimate analysis, or how to calculate the GCV or NCV net calorific values of those particular fuels, and how to mass balance those fuels, that how much amount of fuel we are going to require in the particular operation, and how much flue gases we are going to get due to the burning or consumption of that particular fuel. Okay, so in this week lectures, we first talk about the mass and heat balances for combustion heat utilization furnace, then calculation of gross available heat values available during any fuel consumption for a specific process requirement, then fuel savings on using heat exchangers. So in the previous week lectures, we have also learned about different types of heat exchangers, so that we because so why we are going to require these heat exchangers during the operations or metallurgical operations, because whatever the flue gases which is coming outside during these particular operations, those flue gases can have a temperature of around 1000 or 1100 degrees Celsius based on the furnace temperatures. If furnace temperature is at around 1600 or 1700 degrees Celsius, then flue gases can acquire a temperature of around 900 or 1000 degrees Celsius, or if it is having a lower temperature of around 1200 or 1300 degrees Celsius, then flue gases can have a temperature of around 600 or 700 degrees Celsius. So, as we learned that these flue gases contain some amount of CO and CH4 gases based on the fuel consumption, whatever we are going to use in that particular furnace. So, these flue gases is still having some calorific values. However, they are also having a temperature which is acting as a heat loss during the whole process. Okay, so with the help of these heat exchangers, we can recirculate that heat which is coming out with the help of these flue gases. So these flue gases, we are going to pass them in the heat exchanger. Then, due to the temperature difference between the heat exchanger and these flue gases, the temperature is going to get transferred into the heat exchanger, and then again we are going to pass uh, fresh air or fresh air or fresh excess gases which we are going to require for the furnace operations, so that they can acquire the temperature from the heat exchangers. So these were the works for the heat exchanger. So now we will talk about the heat utilization in furnace. We will talk about some numerical examples, like a furnace which is using coal, and the composition of that particular coal is given. So the air used for combustion. So we have to also talked about we had also talked about the excess air requirement for the proper combustion of any fuel. We had talked about the stoichiometric gas calculations. Then we calculated then we had talked about the excess air requirement for that particular fuel consumption. So now we want to calculate the gross available heat for per kg of coal combustion when the process temperature is around 725 degrees Celsius and 925 degrees Celsius. Then we have to calculate the fuel consumption for the process for these particular temperature ranges. If process heat requirement, this is given at around 2500 kilowatt, then calculate fuel consumption if the combustion heat is preheated with the heat recovered from POC by using a heat exchanger giving having 60% relative efficiency for the process. Okay, so first of all, we will see the specific heat. So we have given the specific heat capacities of the flue gases, like CO2 is having 7.61 calorie per mole degree Celsius. Then CO and N2 is having some specific heat capacity. So now first we calculate the air requirement for that particular heat for that particular fuel combustion. So as we know, we are going to combust 1000 kg of coal for the process, and we have the composition of the coal. So based on that, we can calculate the stoichiometric stoichiometric air calculation for the proper fuel consumption, and then excess air according to the 20% excess air. So air requirement is around O2 equal to 83.4 and N2. So no sensible heat in air. Then POC. Then we can calculate the net calorific value of the coal based on these composition by the help of the Dulong's formula. So we came to know that NCV of coal is coming around at 6851.56 kilocalorie per kg. Then now we can calculate the sensible heat in POC. So for that also we can use the empirical formulas we have learned in the previous week lectures. Then we can calculate the sensible heat based on these empirical formulas. Then sensible heat in POC from 1 kg coal. Then after that we can calculate the gross available heat for the for the particular operation at particular temperature. So gross available heat will be like 68 NCV minus the sensible heat generated at 725 degrees Celsius and 925 degrees Celsius. So gross available heat we can calculate uh, according to that. Then we can calculate the preheated air temperature, which is not given, but sensible heat in preheated due to use of heat exchanger can be found from relative efficiency equal to 100 into sensible heat in preheated air divided by sensible heat in air at hot flue gas temperature. So, with the help of these formulations, we can calculate the whole mass balance of the heat generations by the particular fuel combustion during a process. So, we for these calculations, we require some empirical formulas like Dulong's formula or sensible heat calculation formula. Okay, so that we can calculate. Okay, now we come. So now we will talk about the different types of furnaces which are basically used during these different metallurgical operations. Then what are their functions and what are the working temperature of these different types of furnaces. We will talk about that. Then the furnace classification based on the energy sources and selection of furnaces there are some factors based on which we select the different types of furnaces according to our need during the metallurgical operations. Then, so what is basically defined as a furnace? So the furnace or oven could be defined as a chamber or working enclosure where higher temperature with suitable atmosphere is maintained. Why we are talking about the suitable atmosphere? Because depending on the different types of heat treatment operations or different types of metallurgical operations, we can we need different types of atmospheres. Like we can go for inert atmosphere with the help of nitrogen or argon gases, or we can go for sulfur atmosphere or oxidative or reductive atmosphere. Whatever the atmosphere we are going to require depends on the process what we are going to need. With acceptable thermal efficiency and economy for the conduction of some operations related to industry, research, or domestic life. So there are different the features of furnace can be divided as the furnace purpose. So there are three different types of furnace purpose, like physical, which is generally used for heating or melting purpose. Then chemical, uh, generally used for calcination, roasting or smelting or conversion of any material. Then there are physiochemical purpose, which is basically defined. The proper example for that is sintering. Then furnace temperature we have to define, like low temperature furnaces can be defined as working below 1000 degrees Celsius, then high temperature 1400 degrees Celsius, then very high can be defined which are working at a temperature of around 2000 degrees Celsius. Then there are different types of energy sources used in these furnaces, like coal, coke, oil, or chemical reaction fuel gases or electricity can be used. Then furnace shape can be rectangular chamber or circular tower or long chamber rotatory drum type. And then furnace materials like refractory material combination to sustain high temperature, like acidic refractory or basic refractory, uh, which is which we are going to define according to our need. Then materials handling, like furnace charging and discharging operations, how we are going to perform them. Then air supply, like natural chimney, force induced combined rod. Then like there are operations like batch, continuous or periodic operations, energy conversion methods, heat transfer modes like conduction, convection, radiation or combined. And nowadays we talk about the microwave also, heat in the case of heat transfer mode. Then furnace atmosphere, oxidizing, reducing or inert, furnace working temperature. So when we talk about different types of furnaces and their work, we mostly the common example for a furnace is blast furnace, which is generally used for the of, for the production of the pig iron, pig melted iron. Uh, which is having a temperature of which works at a temperature of around 300 to 2000 degrees Celsius in the different zones. Then there are lime kiln, which is basically used for the calcination of limestone. Then there are coke oven used for the coke making process with the use of the coking coal material. Then there are LD converter, which are basically used for the refining of pig iron to the steels. Then electric arc furnace, induction furnaces, which generally use the electric energy as a fuel source. Then there are billet reheating, or we can say heat treatment type furnaces, which generally use oil or gas as a fuel source. Then there are fluidized bed roasters, which use uh, sulfur itself as a fuel source, which provides some exothermic reactions during the processing of the copper ore, and it provides the energy to the reactor. Then multiple hearth furnaces, same. Then DRI kiln, which use pulverized coal for production of the sponge iron, or we can say direct reduced iron. Then there are some unit processes and the furnaces particular unit processes and the examples of furnaces used for those particular unit processes. Like for carbonization, the main purpose is conversion of coal to coke, and we use generally coke oven for the furnaces, and the energy source is indirect heat of by burning fuel. While in the case of calcination, we generally use the rotary kiln type furnaces and um, energy source by using fossil fuels. Then roasting furnaces are there, which generally convert sulfide ores into the oxides. Generally, these roasting type of furnaces we generally use for the processing of the copper sulfide ores to convert them into the copper oxide, so that we can further go for the smelting processes. Then there are heating furnaces, sintering furnaces, which are generally used for the then electrolysis of molten salt, which is generally used for the production of aluminium, magnesium, and sodium metal from their particular ore source. The common example of electrolysis furnaces, Hall Herold cell. Then there are refining furnaces like LD converter and electrical furnace, which generally use chemical and electrical energy as a fuel source. Then matte smelting is there, which generally used in the refining, which used during the refining of the copper ores, which uses chemical and fossil fuels as a energy source. Then reduction smelting furnace, converting furnace. So there are different types of furnaces based on their different features. Now we will talk about the classification of furnace based on their energy sources requirement. Like there are coal-based furnaces, which uses coal as an energy fuel source. Uh, the common examples of these types of furnaces are boiler house furnace, cement kilns, sponge iron, which generally used for the production of the DRI. Then oil-based furnaces, which generally used for the calcination purpose or the heat treatment purposes. Then there are gas-based furnaces like coke ovens or soaking pits or reheating furnaces, which is generally used for the heat treatment processes. Then there are some electricity-based furnaces like electric arc furnace, induction furnace, which can be used for the refining purpose or can be used for the remelting of the metals. Then there are chemical energy based furnaces which generally use the exothermic reactions happening during the operations as a fuel source. So these furnaces, the typical example of these furnaces are like LD converter, which uses exothermic reactions during the refining of the steel pig iron into the stainless steel making. Then there are the furnaces which generally use for the production of copper, zinc, and lead sulfide concentrates, which uses exothermic reactions, which helps convert the sulfide ores into the particular oxide metal oxides. Then, based on the various shapes for better heat and mass transport classification, we can divide the furnaces in shaft furnaces, which uses a long kiln. Uh, And the common example of shaft furnaces is blast furnace, cupola or mid-rex sponge iron furnaces. Then rotating kilns are there, which are generally which are basically a type of shaft furnace which is horizontally laid. Then there are retort furnaces, rotary hearth furnaces, which is basically used for the DRI making process. Then hearth furnaces are there. Then based on the basis of classification, so we can on the all classifications we can divide the furnaces into like heat sources, fuel used, heat transfer, heat saving appliances, charging system, mode of operation, draught system, say purpose, charges, handling. So there are numerous number of things or factors we can say or applications on which basis we can divide the furnaces into different categories. Then now there are some factors which we need to consider for the selection of a particular furnaces, because we have talked about the numerous types of furnaces like shaft furnaces based on the different fuel sources, based on their shape, size, and operations. So how to select a particular furnace for for the applications. So there are some major factors which involved during the selection of furnaces. Like there are environmental first major factor is environmental laws. So we have to keep in mind laws related to disposal of solid waste. So how much solid waste, like solid waste, liquid or gaseous discharges are getting generated during that particular furnace operation. So we have to keep that thing in mind. Then there are, when we talk about furnaces, so we talk about very high temperatures. So we need some cooling water for the availability of right quality water in required amount has to be there. Then furnace cost and maintenance cost are there, depends on the skill of working and melt practices. So then there are thermal efficiency dependent on the mode of heat transfer and operating practice. So like um, thermal efficiency, like when we talk about the heat treatment operation, so we cannot go with the harsh furnace or some chemical reactive furnace, chemical reacting furnace. We have to provide the fuel source based fuel source as oil or gas material, so that we can get proper thermal efficiency during the operation. Then product quality and contaminations by suitable fuel and furnace selection, floor space requirement, energy source availability, transportation and cost of that particular energy source, like what type of energy source we are trying to use in that particular furnace. Like if you are talking about blast furnace, so we need a lot of coke for the for running that blast furnace, and how we are going to get that coke transported from somewhere else to the particular place where we are going to build that blast furnace, so that we have to keep in mind. Then furnace instrumentation and accessories, the feasibility of adopting them for better furnace control and thermal efficiency. So now we will talk about the producer gas unit. So non-coking bituminous coal is burned partially by limited air supply and steam to generate gas rich in CO, H2, N2 hydrocarbons in the fire clay bricks lined shaft type cylindrical furnace, with the reactor is having three major sections, continuously rotating charging system and gas outlet, shaft air blowing with ash disposal. So producer gas unit basically is defined as a furnace which generally used for converting the non-coking bituminous coal in the gaseous content, which can be reused as a fuel source, because we are trying to convert that bituminous coal into the carbon oxide, carbon monoxide, and hydrogen gases, which can be which is having some calorific values and can be reused as a fuel source. So why we are trying to convert that non-coking bituminous coal into the gaseous content? Why we can't use them directly? Because the major the main property of the non-coking bituminous coal is very high amount of ash content inside these particular coal material. So when we are talking about these non-coking bituminous coals, that can contain a ash percentage of as high as around 40 to 50% sometimes. So if you are going for the direct use of these coal as a fuel source, so we are going to generate a lot of we need to handle a lot of amount of the ash content. Okay, so what we are trying to do with the help of this producer gas unit, we are trying to convert that non-coking bituminous coal into the gaseous content that will be easy to get transported in the plant and can be reused as a fuel source for the different types of furnaces. Like if we are talking about the solid source, then we can use that solid source fuel in the in some particular furnaces only. But if we are going to convert that solid fuel source into the gaseous fuel source, okay, so the the range of the furnaces which can accommodate this gaseous fuel source can get big higher. Okay, so then, then there are some drought operations created during the furnace operations. The pressure required to supply air to a furnacer and to remove the flue gases from the furnace is called drought. So drought is usually expressed as mm of water gauge, mm H2O equal to 1 mm H2O equal to 9.8 Pascal, or we can say 9.8 into 10 to the power minus 5 ATM. So there are three types of rod created in the furnaces for the supply of air or to remove the flue gases from the furnaces. One is natural rod. Natural rod is produced by a chimney and gas flow is controlled by dampers. Then artificial rod is there, so it is produced by fans, blowers or exhaust, and is controlled by the speed of the fan. So we can control the rod according to the speed of fans, variation in the pitch of the fan blades, or by dampers. So the artificial drought can be created in different forms. The natural draught of a chimney is limited, so draught for large furnaces is supplied by fans. Natural draught operates entirely by suction, that is, the chimney sucks or induces the flow of air or gases through the furnace. Then artificial draught may be employed as induced draught. In the induced draught, we generally install a fan at the base of the chimney to augment the natural draught of the chimney under suction. The draught from the fan overcomes the resistance of the fuel bed to the passage of the air, so we can supply the proper amount of the excess air or the air requirement which we are going to require for the proper combustion of the fuel. We can employ with the help of the induced draught process. Then there is forced draught. In this type of process, a fan is installed below or in front of the grate to force primary air under pressure through the firebed and secondary air over the grate. So, with the help of primary air, we are trying to provide the proper air requirement for the combustion of the fuel. And with the help of the secondary air, which we are going to provide over the grate, we are trying to push the exhaust gases outside the system with the help of this secondary air. Then there is balance draught. One fan is installed at the base of the chimney and another at the front end of the furnace. The pressure and suction effects of the fans balance in the furnace, which operates at or near atmospheric pressure. Okay. So now so we have talked about the type of furnaces and the type of drought induced in those particular furnaces, and how to divide the furnaces based on the different scenarios like fuel source or the type of or the shape of the furnaces or the requirement of the application particular application for particular furnace. So now any furnace can if we are talking about any furnace, so it cannot be operated without the help of the refractory material. So refractory is a material which can withstand high temp, because when we are talking about furnace, so we generally talk about a temperature of a magnitude of 1000 to 3000 degrees Celsius generally. Okay, so if we are if we talk about the day-to-day use applications, we generally in the most of the applications we use mild steel. Okay, and mild steel is having a melting temperature of only 14 or 1500 degrees Celsius based on the carbon content inside that particular mild steel. So now we are in the case of furnace, we are talking about a temperature of 2000 or 3000 degrees Celsius. So that is evident that this mild steel cannot uh, sustain that particular temperature for making the for making it to the furnace application. So for making the furnace, we require this mild steel coated with some refractory materials. Okay, covered with some refractory materials. So we are going, we generally go with the different types of refractory materials which can withstand a temperature of up to 3000 degrees Celsius without degrading or softening. Okay, so that these refractory materials are sustaining that particular temperature and creating a safe environment for the outside walls of the furnace, which are generally made up of the mild steel or some other steel, or maybe we can make them some with the help of some other metals. So refractory materials includes ceramics like fire clay, alumina, magnesite, chrome, magnesite, etc., and superalloys and carbon. They minimize heat losses to conserve energy resources. Then refractory materials are produced to meet the diversified requirements, that is, as metallic vessels are neither suitable nor economical. Requirements of high temperature processes like smelting, melting, conversion, heating, and carried out in metal extraction, cement, glass making, manufacturing, or ceramic industries. So reaction chambers constructed with refractory materials sustain the physiochemical attack of different phases at different temperatures for long duration. So the refractory material can be divided into the different The refractory material, based on their chemical nature, can be divided into the three different categories. One is acid refractory, which is generally used for the acid refractories are those which are attacked by basic slag, and it can be used in furnaces having acidic environment. For example, silica, alumina, aluminosilicate, fire clay, or hydrated acid hydrated material refractory can be used as a acid refractory. While the basic refractory is vice versa to the acid refractory, which are generally used for the uh, when there is an attack from the acid slag and used for furnace linings where the environment is basic. So, for acid refractory, we generally use them when the slag chemistry is acidic in nature, while basic refractory we use them when the slag chemistry is acidic in nature. So, the basic example for these basic refractories are magnesite or magnesite chrome or chrome magnesite bricks. Then there are natural refractories. These refractories are attacked neither by acid nor by basic slag. For example, there are graphite, which is having very high refractory value that can sustain a temperature of up to around 2400 or sometimes 3000 degrees Celsius with some modification, with some minor modification. And they are naturally available materials which can be used as a refractory materials. Then there are chromides and synthetic refractories like zirconium carbide and silicon carbide, which can sustain a temperature of up to 2500 or 3000 degrees Celsius based on the chemistry of these particular refractory elements. Then these refractories can be further divided into So there are some special refractories material like especially manufactured using pure synthetic grains for special purposes like fabrication of crucible, some parts of furnaces and research and development, thoria, made up of thoria. Then insulating refractories are there. Then there are cermets. Then based on the saved fibrous and monolithic material also we can divide these refractories into the further applications like shaped refractory specific brick shape used to line surface, kilns, cupola, blast furnaces, etc. Then there are fibrous refractories or ceramic fibers. Then there are unshaped refractories. So phase encountered by refractories like important phases in contact with refractories with having high temperature during the high temperature processing. So there are different materials which can react with these refractories during the high temperature processing or applications. So, number one is slag chemistry. Whenever we talk about the smelting or any smelting operation, so generally we talk about the liquid metal and slag material. Okay, so slag material can be having different natures, like it can be acidic or it can be basic in nature. So, based on the nature of the slag, we have to decide the refractory material. Like for acidic slag, we generally need acidic refractory, like alumina or silica material. And if we are having basic slag, okay, so we are going to require the basic refractory material like magnesite or dolomite, so that they cannot get so the slag cannot get reacted with the refractory material, uh, leading to the distortment of the refractive material during the high temperature applications. So, mixture of molten oxides, sulfide and or phosphates. Oxides are either acidic. Among sulfides are prominent phases of molten slag temperature and different processing lay within 1200 to 1600 degrees Celsius. Then there is liquid metal. So extracted metal in the liquid state, hot metal is a mixture of iron, carbon, silicon, manganese, and phosphorus in between 1300 degree to 1600 degrees Celsius. If we talk about the pig iron molten metal. In copper making, the temperature are within the range of 1100 to 1200 degrees Celsius. Molten aluminum is produced at 700 to 750 degrees Celsius. So based on the liquid metal requirement, and their particular melting temperature. We are going to decide what type of refractive material we are going to use in particular furnace, because there is no sense you are going to use a 1600 or 2000 degrees Celsius refractive material in the manufacture when we are going for the uh, melting of the aluminium, because it generally have a melting temperature of only 700 to 750 degrees Celsius. So while in case of pig iron formation, we require a temperature of around 1500 to 1600 degrees Celsius. So based on these things, we have to decide our refractive material. Then there is matte, which is basically a mixture of molten sulfides like Cu2s, FeS, Ni3H2, etc. And it generally is melt at it generally have a temperature of around 1100 to 1250 degrees Celsius. And as we are talking about the sulfide source, okay, so we generally talk about the acidic refractories, because this matter is having acidic nature. So we are going to require the acidic refractories for the particular requirement. Then there are gases which are going, some gases are also there which are going to get reacted with the. Then spices, which are basically the molten solutions of arsenides and antimonides, which are going to get reacted with these refractive materials. Then drosses are there, which are basically heterogeneous mixture of precipitated solid and liquid compounds formed during refining. So properties of refractive material, how to determine the properties of the refractive material and how to test them. So there are some tests which are required for to check the ability of particular refractive materials, like they can, if they can withstand high temperature or refractiveness. So there is one test like which is called as pyrometric cone equivalent test, which is generally used for the high temperature checking of the refractive material. Then with this how porosity or resistance to attack test is generally uh, performed for evaluating the corrosive action of slag and hot gases on the refractive material. Then withstand abrasion and erosion by moving solid charge, flowing liquids, and blowing gases. Generally test with the help of the strength, wear, modulus, or rupture or porosity. Then refractiveness under load or porosity, which is generally used for checking the withstand working load during service of the refractive material. Then there are some other tests like conduct heat, resist heat flow, sustain repeated thermal cycling, sustain thermal shock, store heat in the system. So okay, so these are different types of refractive materials which are generally used during the different furnace operations. So industrial refractories are hardly ever pure. They do not have sharp melting points, but rather a softening region. The softening region is determined by the phase diagram for the main component and impurities added component, which differs greatly due to the formation of high melting intermediate compound and distribution of impurities and equilibrated non-equilibrated. So okay, that is MC. Yeah. So how to test the refractive material? The high temperature behavior of the refractive is tested by measuring the following properties like PCE, pyrometric cone equivalent value. Then there is refractiveness under load value, creep at high temperature modulus of rupture, thermal shock resistance, which is generally tested with the help of Spaulding test or loss in MOR strength, reversible thermal expansion, PLC, which is known as permanent linear change test. PLC percent linear increases decrease in length or original length into 100. Then PLC volume can be determined with the help of increase or decrease in volume divided by original volume. So pyrometric cone equivalent test. This is generally refractiveness is the measure of the refractory's ability to sustain high temperature without fusion or deformation. It is measured by heating a standard size cone made of the material to be tested in a furnace along with another standard cone having refractoriness very close to the test material, which is determined by a pre-test and finding the temperature at bending 9 or 3 o'clock position viewed upside down of the cone due to its own weight. Okay, so with the help of this pyrometric cone equivalent test, we can check the high temperature sustainability of a refractive material. So the PC value as ASTM code number for common refractive bricks are for alumina bricks it is around 50%, while okay. So for the different composition we have a different ASTM code numbers with the help of which we can calculate the PC value of the any material like 100% if alumina bricks are having 100% alumina content that can sustain a temperature of around temperature of around 1975 degrees Celsius and having a ASTM cone numbers of 42. Then as we can see, as we are going to increase the percentage of the alumina in the refractive bricks, the sustaining temperature of those alumina bricks is getting higher and higher. Like 50, if we are going with a 50% alumina bricks, that can sustain a temperature of around 1650 degrees Celsius. While we talk about 100% alumina brick, that can sustain a temperature of around 2000 degrees Celsius. So according to our need, we can conclude the we can differentiate or we can conclude the composition of the different refractive materials, or we can design the refractive material according to our need with the help of mixing different types of refractive element. Then there is refractiveness under load test, uh, which is test with the help of a equipment which contains furnace which working temperature till 1700 degrees Celsius and heating element made up of supercanthal alloy. Then test temperature, test atmosphere can be ambient air, inert gas or optionals, and loading range 1 Newton to 2000. So in this type of test what we are trying to do, we are trying to compress or we are trying to load the refractory materials at the higher temperatures. First we are going to heat that particular refractory brick which we are going to test, then we are applying the load on that refractory brick and we are trying to uh, check the strength of that particular refractory material at higher temperature. Then creep test at high temperature. It is similar to the above this. It is similar to the refractiveness under load test. It's like similar to the creep testing and UTM, or we can say hardness testing, as we done in the alloy samples, or we can say different metal samples at room temperature. But in case of refractive material, we are performing the similar test at the elevated temperature at around 1000 degrees Celsius or 2000 degrees Celsius according to our need. So, refractive manufacturing processes can be defined as refractive manufacturing process basically consists of four steps. So, generally, when we talk about these refractive manufacturings, so some refractive materials are common found in the natures like graphite. We can easily found in the nature, which can sustain a temperature of around 2500 degrees Celsius or sometimes 3000 degrees Celsius also. If we are talking about the inert atmosphere, okay. So now, if we need a refractive material for some particular conditions, so we have to produce that refractive materials according to our need by mixing some naturally occurring refractive materials like quartz, magnetite, dolomite, chromite, or bauxite in the in some defined fraction according to our need. So, with the help of that mixture, we can create the properties what we are going to require. Okay, so refractive manufacturing process basically consists of four steps. First is raw material processing. So it involves crushing and grinding. Like we are trying to make these particular elements in the powder form so that we can mix them properly. Of raw materials, followed by their classification, vibrating screen trommel, and Then raw materials sometimes need washing, calcination, and drying to meet the chemical specification. The dry refractive powder of one size is mixed with other size to meet specific grain size distribution to have desired porosity and density. Okay. Then there is shaping. The dry powder is mixed with water and other additive to prepare wet dough by with the help of the kneading machines for giving shape to the refractory using different machines like mechanical, hydraulic, vibration, isostatic, or extrusion press can be used. And shape refractory is air dried before the firing operations. Then we generally go with the firing operations. The shape refractory is fired to heat, harden, and stabilize due to the phase changes. So during the uh, this firing operation, there will be some phase changes in the refractive materials due to the mixing of the different types of raw material. They are going to get combined with each other. Then we are getting our final refractive material. Then final processing, it includes milling, grinding, and sand blasting of the fired product to give finishing or desired surface quality, and it sometimes impregnation with tar, pitch, or embalming by steel material. Okay, so this is some machineries that's generally used in the refractory making. Okay, so we have talked about the different refractory making material. So in the first week lectures, I remember we talked about different types of ores, okay, and the size of the ores which we are getting from the runoff mines, or we can call it as runoff mine. So the size of ore is having a size of around basketball. Okay, so that basketball ore cannot be sometimes cannot be reused, cannot be used directly in the furnaces for the smelting or whatever the operation we are going to require to produce the particular metal. So during the during the mineral processing operations, when we are trying to concentrate a particular ore uh, by removing the gangue materials inside from that particular ore, so we produce different types of particle size during the crushing and grinding operations. Like these sizes cannot be directly feed into the blast furnace operation or whatever the operation we are going with. So we need to sometimes we need to increase the size of those particular product by agglomerating them in the form of sinter or pellet or briquettes. So when we talk about a particle size of 10 to 40 mm, so that particle size, so for example, if we are talking about the iron ore content, and it is having a blast furnace grade of around 62.5 degrees Celsius at least. Total iron is 62.5 degree, 62.5 percentage. So if the size is in the range of around 10 to 40 mm, so that size can directly fed to the blast furnace or DRI furnace or DRI operation as a lump. So that is known as lump size. Now, if what if we are having a size of what about the size below which is having less than 10 mm size? So that size cannot be directly used in the blast furnace operations. So we need to increase the size of that particular range. Uh, so from zero point 0.1 mm size to 10 mm size, we can agglomerate that particular size into the sinter formation, which can be directly reused as a feed material to the blast furnace operation. So what about the size which is having a size less than zero point 0.1 mm? So that zero point 0.1 mm size, we need to agglomerate it by a pelletization process so that it can increase up to a size of around 10 to 12 mm and can be used in the blast furnace or DRI process operations, or we can use these pellet agglomerates in making the sinter also sometimes. so that we can further increase the size of that particular material, and that can be directly used as a blast furnace operation. So sinter is a irregular shaped solid lumpy product which is formed by partial melting of the ore particle mixture bed having 50 and sinter can be around 50%, more than 50% sinter can be reused in the blast furnace charge. Then pellet is a solid spherical body obtained by pelletizing fine ores materials with the addition of binders like generally we use bentonite as a binder material, then followed by hardening at some heat treatment temperature around 800 or 900 degrees Celsius. So the blast furnace charge can contain around 30% of pellet material. Then there is briquette, which is a prismatic or cylindrical solid formed by mechanical forces with further strengthening, which gain further strengthening by heating process. Uh, but it is having low productivity and strength, and modern stiff vacuum extrusion developed. Then, in case of pelletization process, we need some some pelletizer, and pelletizers can be disc pelletizer or it can be a drum pelletizer. Based on our requirements, we can go for any type of machines. So during the pelletization, what we are doing, we are adding some water content and some binder material inside inside the powder, which is having a size of less than minus 150 micron. And due to the water addition creates a cohesive surface tension that holds the mineral grains together. When the pellets are heated, they disintegrate as water vaporizes. While binders are added to increase the strength of green and prevent the collapse of pellets during heating. Because when we are going for the heat treatment operations of these particular pellets, then these binders are going to develop the strength inside the pellet material. Then additives like we can add limestone, dolomite or hydrated lime as a correction for basicity so that they can be directly used as a blast furnace material. Then anthracite or coke fines are added to reduce the fuel consumption during for induration process in the blast furnace operation. So binders and green pellet formation. The optimum evenly distributed moisture and binder content and particle size distribution are decisive factors for better green pellet formation. Like low cost bentonite, uh, around 0.58% we have to add. Low cost bentonite is an effective widely used inorganic binder in the iron ore pelletizing as it promotes the uh, formation of ceramic bridges between particles. However, bentonite incorporates undesirable contaminants like silica and alumina, which increases the amount of acid gang in the pellet material. This increases the amount of slag formed in iron and steel making process, which add to the energy needs of such processes. So instead of bentonite, some people are going with some organic binders which are based on cellulose and polyacrylamide which are used as an ultimate alternative to bentonite in iron ore pelletizing, mainly because it burns without leaving any residue in the final pellet. And when the disc or drum rotates, the feed material in contact with water spray form nuclei, which grows by accumulation of fresh feed into pellets. So, if we talk about the green pellets formation stage, first there is nucleation, then snowballing or layering, then coalescence, and then again breakage, and then again this coalescence and again so it is going to form a pellet. Then after making the green pellets, so we have to go for the induration of pellets so that they can withstand tumbling and falling during transport and loading inside the reactors, thus to increase in strength. Green pellets are thermally treated in the induration process. So during the induration, first step is drying operation, which happened at around 105 to 110 degrees Celsius. Pellet undergo first drying, where the water in the form of moisture is removed from the pellets in porous ores. So, drying is generally done at a temperature of around 300 degrees Celsius. The maximum temperature reached in the solid phase during the drying steps are approximately 300 degrees Celsius. After drying, pellets undergo firing steps at which temperature may reach around 1350 degrees Celsius. Here, the calcination of all pellets components like ore, limestone, binder, etc., occurs, liberating chemically bonded water and CO2. Additionally, the sintering of ore grains also happens, leading to the development of mechanical strength. Then sintering may be caused by solid-state interaction of particles and next formation between ore grains followed by pellet densification, but also with the presence of liquid phase, which act as transport and bonding media. The presence of liquid or semi-liquid phases is more pronounced in flux pellets where acid constituents like SiO2 and Al2O3 from the ore may react with basic CO and MgO fluxes and form liquid slag. So generally in case of induration process, we generally go with the straight grade induration process, which um, which includes the different heating zones for the induration of the pellets. Okay, then there is one great thing. Then briquetting, which is also known as cold agglomeration process. So fines generated from the excavation and enrichment of ores. Uh, Containing 70% are of minus 10 production of sinter and pellets, preparation and introduction of the charge in reactors, gas cleaning of exhaust gases, coke making, mill scale can be used as briquette mixture. The most important metallurgical properties of the briquettes are cold strength, porosity, reducibility, softening, and hot strength. While poor lump forming capacity, which negatively affect the quality of sinter, is not a limitation during briquetting. Then ore or coke briquettes based on hematite ore, which contains 79% ore, 15% coke fines, 5.5% Portland cement, and 0.5% bentonite can be used as blast furnace charge. Before the advent of vibro pressing and the technology of steam vacuum extrusion, roller presses were most widely used for briquetting in ferrous metallurgy. An increase in the Fe content in the blast furnace charged by 1%, the productivity of the blast furnace increases by 2 to 2.5%, and the specific coke consumption decreases by 1 to 1.5%. So briquetting, when we talk about briquetting using roller presses, briquetted mixture is fed into the gap between two rolls containing symmetrically located cells in the form of semi-briquettes in a checkerboard pattern. Rotating towards each other during the rotation of the rolls, there is a convergence of cells. The capture of the materials and its sealing bilateral compression. As the rolls rotate, the cells diverge and the briquette drops out. Then briquettes using vibro pressing, briquettes using stiff vacuum extrusion. So there are some process which generally used for briquette making. Okay, so these were the lectures from previous week. So now we will go with some MCQ problems based on the previous week lectures. Okay, so first one is match the following. So there are some nature of operations and their particular examples. Uh, furnace nature operations. There is physical operation, then chemical and physiochemical. So, so when we talk about physical operation, we talk about there should be no change in the physical qualities of particular. When we talk about the physical operation, we talk about there should be no change in the physical properties of any material. When we talk about the physical operation, we talk about like smelting process. Then there is chemical changement. Chemical operation is like roasting and calcination because the composition of that particular compound is going to get changed. Then physiochemical operation is like sintering. So, coming to the next question. There are some furnace types and their particular fuel source. What types of fuel source we generally use in these particular furnaces. So, when we talk about the blast furnace, okay. So, in the blast furnace, we generally use coke material as a fuel source. While in rotary kiln, which is generally used for the production of the direct reduced iron, use pulverized coal as a fuel source material. While induction furnace, or if we talk about the electric arc furnace, they generally use electricity as a fuel source. Then there are alumina kilns which use oil as a fuel source. We talked about the different types of furnaces and what type of fuel source they are generally using. Then there are some unit processes, and for those particular unit processes, what type of furnaces are being used. When we talk about the roasting process, roasting is generally done for the conversion of the metal sulfide ores into the particular metal oxides. The common example is copper sulfide, a conversion of copper sulfide and zinc or lead sulfide into the respective metal oxides so that they can be used for the further smelting operations. When we talk about this roasting operations, these roasting operations is generally done with the help of this multiple hearth furnace. Then electrolysis of molten salt. We talked about the production of aluminium and magnesium in the Hall Herold cell. Then matte smelting is there, which is generally used done in the with the help of the flash smelter, and then reduction smelting is uh, blast furnace. The common example of reduction smelting is like your lead, lead and zinc oxide reduction to this particular metals, and the most common is iron ore conversion to the pig iron with the help of the blast furnace. The major factors involved in the furnace selections are, when we talked about the factors which are involved during the furnace selections, we generally look for the thermal efficiency of the particular furnace for particular operations. Then cooling water requirement, yes, it is there. Then there are environmental laws also there. Answer is all of the above. Match the following. We talked about the different types of droughts and how to create them and what are the particular significance of that drought type. First one was induced drought. So when we were talking about the induced drought, so in the induced drought, the drought from the fan overcome the resistance of the fuel bed to the passage of air. That was this. Then forced drought, force primary air under pressure through the fire bed and secondary air over the grate. Then balanced drought was which was operating at or near atmospheric pressure. Which of them is a refractory material? Magnesite, superalloys, mild steel, or none of the above. When we were talking about the refractory material, magnesite is a type of your basic refractory material which is generally used for when we are going to produce the basic slag during the smelting operations. Then there were some superalloys also, which can be used as a refractory materials like when we talk about 1000 or 1100 degrees Celsius applications. We can go with the inconel alloy or some high nickel containing alloys which is generally known as a super alloy, which can and these types of alloy can be used as a refractory material during a temperature range of 1000 or 1100 degrees Celsius. The common examples of using these superalloys as a refractive material is the coating on your thermocouples. So when we um, need a thermocouple which can sustain a temperature of around 1100 degrees Celsius or 1200 degrees Celsius, but we don't want to get that thermocouple in the contact with the uh, heat source, or we can say whatever the type of material we are going to use in that particular furnace or melting operation. So we generally use this inconel type material as a coating on that particular thermocouple material so that it can be separated from the smelting or whatever the material we are going to melt inside that particular furnace. And mild steel, it cannot be used as a refractive material, although it is having a although it is having a temperature of around 1400 or 1500 degrees Celsius. So why we can't use them as a as a metal coating on that particular platinum thermocouple? Because mild steel is having very is not chemically inert in the nature. It can react with that particular melt, and the thermocouple can get damaged. While the superalloys is having some inert reactions with the particular metals. Then match the following type of refractory and their particular examples. So basic refractory, which are generally used when we are going to make the basic slag during the smelting operation. So the common example of basic refractory is dolomite, which is basically a mixture of magnesium carbonate and calcium carbonate. Then acidic refractory, which is generally used as a uh, refractive material when we are producing the acidic slag during the smelting operation. So common example of this acidic refractory is silica and aluminosilicate. Then there are some naturally occurring refractive materials like graphite is there, which can sustain a temperature of 3000 degrees Celsius. Then there were some synthetic refractive material, which were zirconium and chromate. Refractive materials should have the ability to withstand corrosive action of slag and hot gases. Yes. Then they should have high thermal conductivity. Yes. Sustain repeated thermal cycling. Yes. Okay. No. High thermal conductivity should not be there. They have to be inert. They have to be. They have to have very low thermal conductivity. So heat losses should not be there. With the help of these, the major use of refractive material is for reducing the heat losses during the operations. Which tests are done to determine the high temperature behavior of the refractive materials? So, do we go with proximate analysis? No, the proximate analysis is generally used for determining the carbon percentage and volatile matter percentage in any fuel source. Then there is pyrometric cone equivalent value. Yes, this is generally used for the testing of high temperature properties of a refractive material. Then there was spalling test, which is generally used for checking the strength of the particular refractive material. Then loss on ignition. No. Okay, so this is for today.